We start with basic differentiation with the full knowledge of limits of a function, because they are related in the sense that the derivative of a given function at a particular point is equal to the gradient or the slope of the tangent of that curve at that particular point. And we know the derivative of a given function is given from basic principles by that limit of f of x plus h minus f of x all divided by h as h approaches infinity. That is why you see that I've written there m tan, which is the slope or the gradient of the tangent to the curve. Note also we have different notations for the derivative. It could be dx, or it could be d over dx, or it just could be y prime or f prime. So we have that final notation that we're using at the bottom, where you must realize that the gradient or the slope of the tangent is just equal to the first derivative of the curve at the point of contact. Here are some examples where we use the definition of the derivative. Every time you are asked to find the derivative of a function from first principles or by using the definition, you must write that formula: f prime of x equal to the limit of f of x plus h minus f of x all divided by h as h approaches infinity. Now f of x plus h, in the given formula for your f of x, wherever there is x, you substitute x plus h. I cannot stress it more that your simplification and removal of those brackets when you substitute x plus h into your f of x is very important. Also, note that we have here minus f of x. You substitute the given function. If it's got two terms, please make sure that you use brackets so that the negative will be able to affect both terms. If you've got more than one term, it has to affect all the terms of f of x. So please make sure that when you remove the brackets, the negative has been used on both the terms of f of x. Also, please perfect the simplification of binomial squared, trinomial squared, because you need that knowledge, which you did in previous years. And then you cancel out the terms that similar, like for instance 3x and negative 3x, they cancel each other out. Which other term? Negative 2x squared and 2x squared. And then you are left with 4x plus h plus 2h squared plus 3h in your numerator. Denominator is h. Note, as long as you have not substituted the limit that has been given for h, you have to always take down lim as h approaches 0 every time until you substitute the limit. As you can see, even the next step, we still have lim as h approaches infinity of our simplified expression. And then take out h from the numerator and then we are left with 4x plus 2h plus 3. And then, and then you will be able to substitute h equal to 0. And then our final answer is 4x plus 3 for f prime of x. Note the final answer after you've substituted the value for h will not have limb. Please take care of that. Also, you may break this whole problem down where you write first step f of x, second step f of x plus h, third step you write f of x plus h minus f of x. You do your simplification and then you bring it all back into the formula, and then you will be able to substitute everything into the second step or the third step, depending on how far is your simplification, and then sort everything out. Here's example 2, where f of x is equal to 4x cubed plus 5 over x. Once again, you write the formula for f prime of x from first principles, and then the next step, wherever there is x in f of x, we substitute x plus h minus our f of x. Note, because our f of x has got two terms, we place that in brackets. Thereafter, do the simplification. I need you to check whether my simplification of x plus h all cubed is correct. And then thereafter, you remove the brackets around the terms of f of x, and then make the whole numerator under a common denominator, which is x plus h, and which is x and x plus h, so that we will be able to do our simplification. I need you to check all the steps and see whether there are no mistakes. As you can see, after the simplification and making the numerator under one common denominator, I took out h, so that h and h will be able to cancel, and then you are left with all the other terms that were in the numerator, and then substitute h equal to 0 in. But in order for you to be able to perfect this, your main aim must be to make sure that you get rid of the h that was given to you in the denominator. That h must be removed, especially if the limit is approaching 0, because you cannot divide by 0 in mathematics. So our main aim for all the simplifications we're doing is to remove that h from the denominator. And thereafter, once it has been removed, you can then be able to substitute the value for h, which is 0, and simplify. And please check whether you'll get the same answer. Now we go to the square root. What if our function has got a square root sign? It means we have to bring in the rationalization that we're introduced to when we were being introduced to square roots. The definition of f prime of x, we substitute f of x plus h. Now we'll have the square root of x plus h minus f of x, which is the square root of x, all divided by h. Rationalize, because your main aim is to make sure that you are able to cancel out h from the denominator. We cancel it with h that is in the numerator. So you multiply out by f of x plus h plus f of x divided by f of x plus h plus x. So that means here we're rationalizing the numerator in this case. Multiply out f of x plus a, the square root of x plus h times the square root of x plus h is just x plus h. Note that this is the difference of two squares that you see in your numerator. So the next term is minus square root of x times square root of x, which is x. Your denominator, no problem with that. And then you're simplifying the numerator, we're getting h and h cancel out, and you are left with 1 over the square root of x plus h plus square root of x. We substitute the value for h, which is 0. The denominator becomes 2 square root of x. You can even rationalize by multiplying by the square root of x, both the numerator and denominator. So your answer, final answer, will be the square root of x divided by 2x. Square root of x divided by 2x will be your final answer. Let me try and write it out here. Square root of x divided by 2x. Now here are some problems that you can do for practice. Please make sure that you check your simplification. Check everything and make sure that everything is okay. Okay, here are some rules that we use. Just the simple rules of differentiation. We start with the first 8, where the first one we know the derivative of a constant is equal to 0. Note that in this case, I just used x as my variable. So all the derivatives are with respect to x. So if you're differentiating x with respect to x, you're getting 1. Please check all these laws. Note that for rule 4, if you are multiplying a function by a constant, you take out the constant and differentiate the function. The derivative of ln of x will always be 1 over x. So that means it's 1 over the argument of ln. The derivative of a square root of x will always give you 1 over 2 square root of x. And the derivative of a sum or difference of two functions will, what you do is to spread the derivative inside. So that means you're differentiating f of x and you're differentiating g of x. Whether it's a sum or a difference, it does not matter. Also, the derivative of an exponential function always gives you the exponential function, especially if it is e to the power x. Note that we're going to introduce the derivative of a to the power x, and then you'll be able to see why, the difference between the two. Also, and then you'll realize that it works even for the derivative of e to the power x. And lastly, the derivative of x power n is equal to n x to the power n minus 1. Let's do some examples and some exercises to apply these few rules. Note there are more rules, more complicated ones as we move. Number 1, the derivative of f of x. Note that that's a constant. The answer f prime of x would be equal to 0. That's obvious. Also, number 2, f of x is equal to 5x minus 1. So we spread the derivative inside, so we're differentiating 5x and we're differentiating 1. So there's a difference of two functions. So the derivative of 5x is 5 times the derivative of x. and the derivative of x is 1. So that means you'll have 5 as your answer for the first term, minus the derivative of 1. 1 is a constant, that is a 0. Number 3, the derivative of the square root of 2 multiplied by x naught. Square root of 2 is just a constant, so you take it out. And then you find the derivative of x. And then when you get to the second term, the derivative of the square root of 3x, we are going to introduce you to the chain rule. The answer to this is 1. Remember, the derivative of a square root is 1 over 2 square root of whatever was the argument of the square root. So that means you are going to have 1 divided by 2 square root of 3x. But now you have to multiply by the derivative of the argument of the square root, which is the derivative of 3x, and that your answer is 3. We're going to get to that because now for the second term, we use the chain rule. We'll introduce you to the chain rule in a little while. Number 4 is the same as number 2, where you find the derivative of each term. The derivative of the square root of x is 1 over 2 square root of x minus 2 times the derivative of e to power x, which is just e to power x. But then we get to number 6. Because we have not learned any other methods of differentiation, it means we have to simplify y first before finding the derivative of y. We know the square root of x is just x to the power half. So what you do, you divide each term in the numerator by x to the power half. And then you get your answer, a simplified version of y, and then find the derivative. Same with number 5, where you take the square root of x as x to the power half, you multiply inside the bracket each term to simplify your f of x, and then thereafter find f prime of x. You do the same even with number 9 as well as number 10. Number 7, you change the cube root. I hope you still remember cube root. It means the power is 1 over 3. So it means the first term will be x to the power 2 over 3 because it was a cube root of x squared. And the second term will be 2 times x to the power 1 over 3. And then we use the rule that involves x to the power n, the derivative of x to the power n. We do the same even for number 8. I'm hoping that we'll be able to manage to do these problems. Let's move. Now we go to the product and quotient rules. These two rules apply when we're asked to find the derivative of a quotient, a function divided by another function, or a product of two functions. Now let's note this. For the product rule, you differentiate one function while the other one goes down as it is, plus the first function times the derivative of the second. So you can interchange. You take down the first function and find the derivative of the second function, plus you take down the second function and multiply that by the derivative of the first. So these two are interchangeable. So whichever you start with, it's okay because it's just a product of two functions. So as long as you remember, find the derivative of one function, take down the other function, plus the other function times the derivative of the first function. So whichever you decide to start with is okay. So it's the first function's derivative times the second function plus the first function times the derivative of the second function, or the other way around. Now, when it comes to the quotient rule, it's a different ball game altogether. Note that g of x is in the denominator and f of x is in the numerator. So what you do first, you take the denominator up. So it's the denominator up multiplied by the derivative of the numerator minus the numerator times the derivative of the denominator. That's what forms your numerator. All of that is divided by the denominator squared. So every time it's denominator up multiplied by the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Let's apply this and let's see if we'll be able to implement them. Number one, we're given a product of two functions. We cannot simplify that. It's the square root of x multiplied by e to the power x. Cannot be simplified. So we take it as a derivative of a product of two functions. So what has happened here? Took down the second function, found the derivative of the first, plus the first function as it is times the derivative of the second, using the product rule. So that means we'll have e to the power x multiplied by 1 over 2 square root of x, which is the derivative of the square root of x, plus the square root of x times the derivative of e to the power x, which is just e to the power x. So even if you would have started with the second term and ended with the second term, you can interchange those. What you do, you take down the first function, which is the square root of x, multiplied by the derivative of the second, plus then you take down the second function, then you multiply that by the derivative of the first. You can interchange those two terms. They are not a problem. Always remember, when you differentiate one function, you take down the other one as it is. For number two, we could have just simply removed the brackets to simplify our problem so that we have a polynomial, but let's just use the product rule for now so that it guides us and we're perfect on how to use it. So the first term, what we did was to take down the first bracket and then find the derivative of the second plus the second bracket times the derivative of the first bracket. So it means we'll have the first bracket, which is 2x cubed plus 3, into the derivative of x to the power 4 minus 2x, which is 4x cubed minus 2, plus the second bracket, which is x to the power 4 minus 2x, times the derivative of the first bracket, which gives us 6x squared. You leave it here unless the instruction has been given that you simplify fully. If it has not been given to you, you leave your answer as it is. Then number 3. Now here we see a quotient of two functions, 3x minus 1 in the numerator and 2x plus 1 in the denominator. Remember, for the quotient rule is denominator up first. So you take the denominator up, multiply that by the derivative of the numerator minus the numerator times the derivative of the denominator. All of this must be divided by the denominator squared. First bracket, 2x plus 1, no change there. You multiply by the derivative of 3x minus 1, which is 3, minus the second bracket, or the numerator, which is 3x minus 1, times the derivative of 2x plus 1, which is 2. All of that divided by the denominator squared. Note, the denominator squared is not a derivative. It's just, you just square your denominator and you leave it as that. Once again, we use the quotient rule for number 4. Denominator up first, times the derivative of the numerator. Derivative of square root of x is 1 over 2 square root of x, minus the derivative of 1, which is 0, minus the numerator times the derivative of the denominator. All of this is divided by the denominator squared. You may simplify based on what the instruction has told you. Number 5 up to number 8 require a bit of simplification and a bit of timing, because for number 5, you may just simply do your multiplication and come up with a polynomial and then find the derivative of the polynomial, or you use a product rule. Note that you have to take y squared up, so it becomes y to the power negative 2 minus 3 y to the power negative 4, which makes life easy when it comes to differentiation. Product rule again for number 7, but for number 6, quotient rule, and for number 8, quotient rule. Attempt them and let's see whether you'll be able to use the first 8 rules that we gave you. Note that product rule and quotient rule is applicable to all kinds of functions that may be given. We may be given hyperbolic functions, we may be given trigonometric functions. It's applicable everywhere. Straight to derivatives of trig functions. Note, sin x produces cos x, but cos x produces negative sin x when we're differentiating. 10x gives you sec squared x, cosec x gives you negative cosec x cot x, and then sec x gives you sec x 10x, and cot x gives you negative cosec squared x. Let's use this as part of our problems. Note that we may incorporate them in any kind of a problem. Quotient rule, product rule, the chain rule, which I'm going to introduce to you soon, and any other problem, it is applicable. We may be able to introduce you to the trig functions. In our examples, as you can see, we've got product rule and quotient rule here. Derivative of 1 up to number 5. Note, you are asked to leave your answers in the simplest form. Now, for the first one, quotient rule. So it will be the denominator up, which is 1 plus 10x, multiplied by the derivative of sec x, which is sec x 10x. So you have 1 plus 10x in brackets into sec x 10x. That is your first term, minus sec x into the derivative of 1 plus 10x, which is sec squared x. All of this is divided by 1 plus 10x all squared, and you simplify. Number 2, quotient rule again. Please attempt it and let's see. Number 3, you have cosec theta plus e to the power theta cot theta. The second term is a product, but the first term is not. So y prime will be equal to the derivative of cosec theta is negative cosec theta cot theta plus. Then you use the product rule. Take down e to the power theta, find the derivative of cot theta, which is negative cosec squared theta plus cot theta times e to the power theta, and then you simplify. So you do all that using what you know of the product rule and the quotient rule and the derivatives of trig functions. And then you please make sure that you simplify all your answers. We've been talking about the chain rule throughout. Now we have to use it. Note that if y is equal to u, but u is a function of x, then it means we have to use the chain rule, because when you're finding the derivative of y, it will be the derivative of y with respect to u, because y is a function of u, but u is a function of x. So it means you have to continuously do the chain dy over du multiplied by du over dx. Guess what it gives you? It gives you dy over dx. Y, if you want dy over dx, y is a function of u, so you differentiate y with respect to u, and then you multiply the derivative of u with respect to x, and then it will give you dy over dx. Let's apply this, because this is what we know is the chain rule, and usually it's applicable to composite functions where you have one function inside another function inside another function. Let's see if we'll be able to understand and be able to apply the chain rule appropriately. Number one, p of x is given to us as 1 minus 3x squared, all to the power 4. So the first thing we notice is that this is a composite function. There's 1 minus 3x squared inside another function. So in place of x, we have 1 minus 3x squared. So it means the original function was x to the power 4. And then we introduced another function. In place of x, we had 1 minus 3x to the power 2. To find the derivative, the first thing we do, we find the derivative of the original or the outer function, the power 4. We use the power rule. We know the derivative of x to the power 4 is 4x cubed. So we use exactly that, taking 1 minus 3x squared as a combo. So that we are saying it's 4 times that combo to the power 3. And then you multiply by the derivative of your inner function, which is 1 minus 3x squared, which gives you negative 6x. So you first differentiate the outer function, and then you multiply that by the derivative of the inner function. I'm hoping that that makes sense. Let's go to number 2. Number 2, we have y equal to sine squared. And the argument of sine squared is another function, e to the power sine squared theta, or sine squared t in this case. So we're looking for dy over dt. So the first thing we do, sine squared has to be differentiated. So the first thing we differentiate is the power 2. So we use the power rule. It's 2 sine. Note that we can't leave the argument of sine out. So it's 2 sine of the argument multiplied by the next thing. So the first thing we did was to differentiate the power 2 of sine squared. And then the next thing we're supposed to differentiate is sine. And we know the derivative of sine is cos. Note that you always take down the argument of the trig function multiplied by the derivative of the argument. We know the derivative of e to the power x is always e to the power x, whatever the value of, or whatever the expression for x is. So the power of e remains the same, e to the power sine squared t. Then you have to multiply the power of e, which is sine squared t. It's supposed to be 2 times sine t multiplied by the derivative of sine t, which is cos t. So it, as you can see, it's a chain of events. So you start with the square of sine, it becomes 2 sine, multiplied by the derivative of sine, multiplied by the derivative of the angle, multiplied by the derivative of the power of your angle, or should I say the argument. I'm hoping that we're together. We go to number 3. Y equal to tan of sine of square root of 1 plus t cubed. So the first thing, the outer function is tan. The derivative of tan we know is supposed to be sec squared. Note, every time you write a trig function, its argument must be there. So we'll have sec squared of the argument of the original function multiplied by. Now we come to the derivative of the argument. The first thing we have there is sine. The derivative of sine is cos. And I'm still writing the argument of sine, which is square root of 1 plus t cubed, multiplied by the derivative of the angle, or the argument. We know we've got a square root, so it's always 1 over 2 square root, whatever is under the square root sign. And then thereafter you multiply by the derivative of the argument of the square root. Number 4. We've got 2 square root signs there. So y is equal to 8 into the square root of 1 plus square root of x. So y prime equal to, you remember you take out the constant 8, then you multiply by the derivative of the square root of 1 plus root x, which is 1 over 2 root of 1 plus root x, times the derivative of what's under the big square root. Derivative of 1 is 0, and the derivative of square root of x is 1 over 2 square root of x. And I'm hoping that you are able to realize, always start with the outer function and then go inwards. Number 5, y is sine of cos of 10x. The derivative of sine is cos, that's where we start. And we must not forget the argument of sine is cos 10x. So we have to take it down as it is. And then we come inside. We have to go for the derivative of the argument of sine. So the first thing we encounter is cos. Derivative of cos is negative sine. And the argument of the original cos was tan x. So that means we'll have negative sine 10x. And then we go to the derivative of the argument of cos, which was 10x. The derivative of 10x is sec squared x. Then we go to number 6. The derivative of ln of cos of 2x cubed. First thing we encounter on the outer part is ln. And we know the derivative of ln x is 1 over x. So ln, when you differentiate it, always take its argument to the denominator. So we'll have 1 over the argument of ln, which is cos 2x cubed, multiplied by the derivative now of the argument. So the first thing we encounter in the argument is cos, so it becomes negative sine. The argument of cos was 2x cubed, so we have to write it as it is. And then we go to the derivative of 2x to the power 3. Then we get 3 times 2x squared multiplied by the derivative of 2x, which is 2. Number 7, we have ln cubed of cos 2x. So the outer function is the cube or the power of ln. So we'll have to have 3 times ln cos 2x to the power 2, differentiating the power, and then differentiate ln, which gives us 1 over cos 2x, multiplied by the derivative of cos 2x, which is negative sine 2x times 2. Let's complicate this, because now for the chain rule, it is applicable to trig functions. It is applicable to quotient rule. It's also applicable to the product rule. So let's bring in the quotient rule in number 8. The numerator is ln of sine x. The denominator is x cubed. Ln of sine x divided by x cubed. Then y prime would be, now we have to use the quotient rule. Take x cubed up. So we'll have x cubed multiplied by 1 over sine x multiplied by cos x. I hope we understand. So derivative of ln is 1 over sine. The derivative of sine x is cos x. So note that we always say denominator up first times the derivative of the numerator minus the numerator times the derivative of the denominator. All of this is divided by the denominator squared. Number 9, it looks more complex. Let's go for it. The first term is the square root of sine cubed, and the argument of sine cubed is the cube root of x. Let's start there. The first thing, find the derivative of the square root sine. It's 1 over 2 square root of whatever was under the square root sine, multiplied by, we go now under the square root sine, find the derivative. The first thing we encounter is the power of sine, which is 3. So we have 3 sine squared of the cube root of x, multiplied by the derivative of sine, which is cos of the cube root of x, multiplied by the derivative of the cube root of x. You need now to confirm that the derivative of the cube root of x is 1 over 3 cube root of x squared. I need you to confirm that for me. Then we go to the second term. Second term is cos squared of the square root of 1 minus x squared. So first thing, power rule. So it's 2 cos of the square root of 1 minus x squared times the derivative of cos, which is negative sine of the square root of 1 minus x squared, times the derivative of the square root, which is 1 over 2 square root of 1 minus x squared, times the derivative of 1 minus x squared, which is negative 2x. Then we go to the last term. We have the cosec squared of x over x plus 1. Firstly, the power of cosec, so we get 2 cosec of the argument multiplied by the derivative of cosec. The derivative of cosec is negative cosec cot, and then we take down the argument, times the derivative of the argument, which requires the quotient rule. So we take the denominator up, which is x plus 1, times the derivative of x, which is 1, minus x times the derivative of the denominator. All of this divided by the denominator squared. So this problem incorporated everything, almost everything that we've learned thus far, except for ln. So I'm hoping that you'll be able to understand it as we go on to more complicated problems. Number 10. I'm hoping that you'll be able to get through these exercises, product rule and quotient rule for number 10. Product rule and chain rule for number 10. And then number 11 is quotient rule and chain rule. And then number 12 is product rule and chain rule. Number 13 is the product rule. Yes, just the product rule. Number 14, it's done for you. It's the chain rule. And then once you've done all these other 14 problems and you understand them, then do those 3 exercises. Kind of complex, but you can be able to manage them. What if then we have a situation where we've got problems or given functions that are not explicit? Explicit, that is, you are able to separate the variables. What if they are implicit? Then it means we have a function of 2 variables that you cannot be able to separate. And they follow a different format when it comes to differentiation. Note that you will always be asked to find y prime or dy over dx for those functions. So the first thing you do, given any expression that is implicit in nature, find the derivative of each term. Now you need to note y is a function of x. So if you are given the derivative, you are asked to find the derivative of y squared. It means it is 2 times y times dy over dx. We use the chain rule on it. So whenever you have a variable y, you have to use the chain rule to find its derivative. And if we've got x times y in your expression, it means you use the product rule because y is also a function of x. So the first step for implicit functions, differentiate each term. Wherever a term has got both x and y, use the product rule. And also wherever there is a term that has got y, you use the chain rule. Then you rearrange all your terms, that's the second step, and make dy over dx the subject of your expression. Let's do a few examples. Number 1, we've got the 3y to the power 4 plus xy squared plus 2x cubed minus 6 equal to 0. First step, find the derivative of each term in your expression. So 3y to the power 4 gives us 12y to the power 3 multiplied by dy over dx, because we have to always take into consideration that y is a function of x, and we're differentiating each of those terms with respect to x. So chain rule applies. Second term is x y squared. X y squared, product rule. So you differentiate x first, you are left with y squared plus x times the derivative of y squared, which is 2y, multiplied by dy over dx. And then the derivative of 2x cubed is 6x squared. Derivative of negative 6 is 0, and the derivative of 0 on the right hand side is 0. Let's do this again. Derivative of 3y to the power 4, we do it using the chain rule. It's 4 times y to the power 3, and the 4 multiplies the 3 that we had there. That's why we have 12. But then we have to remember the derivative of y is dy over dx, because y is also a function of x. And then the derivative of x y squared, we use the product rule, and it gives us y squared plus 2xy times dy over dx. And then the other two terms, 2x cubed minus 6, they just give you 6x squared. The right hand side is 0. Then what you do next, remove the brackets and take all the terms that do not have dy over dx to the right hand side, and then take out dy over dx on the left. Please confirm that inside the brackets there, when we've taken dy over dx out, those are the two terms you'll be left with. Then on the right hand side, you'll have negative y squared minus 6y squared minus 6x squared, and then make dy over dx the subject. Then you have what the two terms that we had on your right hand side divided by the two terms you had on your left, which is 12y cubed plus 2xy. Number 2, we have 2x cubed y plus y squared plus x all to the power 3 equal to x to the power 4. Still, the question says we must find dy over dx. So find the derivative of each term. We have 6x squared y. I'm hoping you understand that, because we have to do product rule for the first term. So I've got 6x squared y, that's the first term, plus we take down 2x cubed and then find the derivative of y, which is just dy over dx. For the second term, we have the power 3 there, so we have to use the chain rule. Use the power rule first. 3 into y squared plus x all to the power 2 multiplied by the derivative of what's inside, which is y squared plus x. The derivative of y squared is 2y times dy over dx, and the derivative of x is 1. And then you have 4x cubed on the right hand side. Make dy over dx the subject. That means all the other terms that do not have dy over dx must go to the right hand side. I need you to confirm this step, that these terms are correct after removing the brackets. And then your final answer, dy over dx, will be given by the last expression. Please confirm that that is correct. Let's do some more and I'll give you more exercises. Number 3, We've been given cot 2x minus 3 cosec xy equal to y squared. Now, once again, we implement what implicit differentiation requires of us. We find the derivative of each term. The derivative of cot 2x is negative cosec squared 2x multiplied by 2. That's why we wrote here negative 2 cosec squared 2x minus 3 into the derivative of cosec xy, which is negative cosec xy cot xy multiplied by the derivative of the argument, which is xy, and it gives us y plus x y prime, which is our, after using the product rule. And then the derivative of y squared, which is 2y times y prime. And then we remove brackets, simplify, and then take all the terms that do not have y prime to the right hand side and all the terms that have y prime to the left. Take out y prime and then make y prime the subject. Please confirm if you'll get the same answer after you have done your simplification. Number 4, we're given y equal to x ln squared of x plus y. Take the derivative of each term as usual. Left hand side is got y prime. Right hand side we have 1 minus, once again, chain rule. We start with the power 2, so we've got 2 ln of xy multiplied by the derivative of ln, which is 1 over the argument of ln, multiplied by the derivative of the argument of ln, which is 1 plus y prime. Remove all brackets. Simplification, please confirm that all the steps are correct and will lead you to that final answer for y prime. Please make sure that you do your simplification properly. Here are some exercises. Once again, you're asked to find y prime. Now we've included the derivative of log and the derivative of a to the power x. Please go through the tables of derivatives to make sure that you understand how to find the derivative of those that we have not used in the examples that we've done thus far. Also note for number 1, you can simplify the left hand side easily so. Let's see what you will get. Now we move on to log differentiation. Log differentiation is used basically for expressions that are very complex and complicated when you're looking at them. They may have products, quotients, powers, and square roots, cube roots, very complicated expressions that you cannot readily differentiate. Now note this, quotient rule is only used when there are 2 functions, one in the numerator and the other one in the denominator. Product rule is used on just a product of 2 functions. Now, if we've got a product of 3 functions, or you have a function divided by a product of 2 more functions, the easiest route is to use log differentiation. you cannot use the quotient rule when there are more than two functions, or you cannot use the product rule when you have more than two functions. So you must always find a different route or a different method to use. Now, log differentiation produces or gives us an alternative. So what you do, we use the laws of logs as a way of simplifying our expression. So what you do, introduce logs on both sides of the equation, simplify the expressions, and then use differentiation. You differentiate each term on the left hand side and then make y prime the subject. And then if your final answer has got y, you substitute the original expression that was given to you, which was explicitly given for y. So let's do some examples, and this whole process, we call it the log differentiation. The first example that we have there, we can see the numerator is a product of two functions, and then we have a denominator. Remember, we cannot use a quotient rule if there are more than two functions in an expression. So product rule and quotient rule cannot be used here. The easiest route, log differentiation. So we introduce logs. So the easiest one to use for us is ln. Introduce ln on both sides, which is the natural log. And remember that the rules for the natural log and the rules for the log base 10 are exactly the same. So we simplify the right hand side. We know when there's a product of two functions, it's addition. And if there's a quotient, you subtract. So it's ln of x squared plus 1 plus ln of x plus 3 all to the power half minus ln of x minus 1. And then we recall that if you have ln of x squared, it's the same as 2 ln x. That is why we have half times ln of x plus 3. And then find the derivative of each term. Remember, the derivative of y, because y is a function of x, will always be y prime. So now we've got ln y, we'll have 1 over y times y prime times the derivative of each term on the right hand side, which gives us 1 over x squared plus 1 times 2x using the chain rule, plus half times 1 over x plus 3 minus 1 over x minus 1. Make y prime the subject. That means y will be taken to the right hand side. And we were given an explicit expression for y in the original equation. So we substitute the expression for y on the right hand side. And we leave it as it is. No simplification required. We just substitute y in. Let's do some more examples as we apply log differentiation. Number 2, we've got cot cubed x times 10x squared all divided by 3x squared plus 1 all squared. That is an expression for y that has been given. So we introduce ln on both sides. We've got ln y equal to ln of the whole expression on the right hand side. And then the next step is the simplification of the right hand side. So we still have ln y on the left equal to 3 ln cot x plus ln of tan x squared minus 2 ln of 3x squared plus 1. I'm hoping that you still remember the simplification of log functions. And then we find the derivative of each term. Ln y gives us y prime over y, and 3 ln cot x gives us 3 times 1 over cot x multiplied by negative cos x squared x. And then the derivative of ln of tan x squared is 1 over tan x squared times the derivative of tan, which is sec squared, and the argument of tan was x squared, multiplied by the derivative of x squared, which is 2x, minus 2 times the derivative of ln of ln of 3x squared plus 1, which is 1 over 3x squared plus 1, multiplied by the derivative of the argument of ln, which is 6x. Simplify, take y from the left to the right hand side, and then you substitute the expression for y on the right hand side in your final answer. Please check my signs, check my simplification if everything is correct. Here are more exercises that we can use log differentiation on in order for us to get y prime. And note that we've been given explicit expressions here, so it will be easy for us to substitute the expression for y in our final answers for number 1, number 3, number 4, number 5, number 7. It will not be that easy for number 2, number 6, and number 8. As you can see, there you have implicit differentiation coupled with log differentiation. So please attempt. So you simply introduce ln and then you substitute. Simplify your right hand side so that we get a simplified expression, and then thereafter you find the derivatives of each term and make y prime the subject. Let's attempt these problems and let's see what we'll get.